I'm now in a very lucky position that Matt just did most of my introduction, so I can focus more on the science. And I'll also have some time to present some new results on hidden variable models and causal modeling afterwards. But first I'll talk about what the title says. So that's the experiment that Matt was referring to in his talk before. So I'll start with this slide again. That's our matrix of interpretations, where up here all Copenhagen type interpretations we're not looking at right now. We look at the interpretations that have some objective reality in it. And there, as Matt explained, we have two classes, the ones where the quantum state is in direct correspondence to reality, and the ones where the quantum state represents some kind of knowledge about that underlying reality. And now, to begin with, I'll repeat a few key points of our theoretical framework, so the ontological model framework that Matt already discussed. So it's basically the hidden variable framework, where we have some ontic state space, like a classical phase space, and every system takes a value in this phase space. Now, if I go to the lab and I prepare my quantum state, my psi, what actually happens is I prepare some ontic state that is sampled from a probability distribution in this ontic state space, which we call the epistemic state. And then if I take two quantum states, I can have these two situations. Either for every pair of two quantum states, I end up with distinct distributions, which means that the quantum state is then in direct correspondence with reality, because if I know the ontic state, the state of reality, then I automatically know the quantum state. So that's what we mean by psi ontic. On the other hand, we could have some overlap here where this is not the case, and that's what we call a subsystemic interpretation. And what we want to do in experiment is we want to make some statement about this distinction here. Now, we already heard that without any additional assumptions beyond this framework, we cannot rule out subsystemic models. But what we can do is we can constrain their explanatory power. So we can constrain to what degree they can explain this indistinguishability that Matt was talking about. So we follow this series of 3 papers, in particular the last one by Branciat, and they have slightly different bounds on this, but they have one statement in common, which is that the limited distinguishability of non-orthogonal quantum states cannot be fully explained by a subsystemic model. For systems larger than dimension 2, so Matt already said qubits are always special, but everything larger than that cannot be fully explained. Now, what we need for this is some kind of overlap measure. And what we use is the quantum trace distance with a metric in state space, and then 1 minus the trace distance gives us our quantum overlap. In the classical case, same thing, we take the equivalent measure for classical probability distributions, and 1 minus that is our classical overlap. So Matt already motivated that with optimal probability of distinguishing those two states. And what is now particularly important for us is this notion of maximally subsystemic models. So when these two measures, these overlap measures, are equal, that means we can explain all the indistinguishability in terms of overlapping probability distributions, which is what we call a maximally subsystemic model. And then our figure of merit in our experimental test is this ratio. So whenever that ratio is below 1, that's incompatible with a maximally subsystemic model. Now, I'll walk you through the actual experimental protocol. So what we do is we pick a set of n+1 quantum states. So we have this one reference state, psi 0, and then n more. Now, all of this has to happen on a system larger than a qubit, so we choose a q quad. And we choose the logical 0 state as our reference. And then if you choose all the other states real valued and project them on the orthogonal subspace, that looks somewhat like this. So that's states that we used in the experiment. Now we can scale this up. That's 7 states. We can go higher. If we take like 13 states, it looks like that. Still very pretty. There's quite some symmetry in there, which is important. And then we pick triplets of states. So we pick all possible triplets which contain the reference state. And for example, like this. And for each of those triplets, we define a 3-outcome measurement. And that might look like that, for example. And then we collect statistics and calculate these outcome probabilities and derive this inequality. So looking at that inequality, we have the numerator, which is an upper bound on the classical overlap. And the denominator is just directly the quantum overlap. So this upper bound is what we get from the experiment. And now this whole quantity is an upper bound on our figure of merit, the ratio between those two overlaps. So it's really an upper bound on how much, in relative terms of the indistinguishability that we observe, can be explained in terms of overlapping probability distributions. And now, S has to be larger or equal to 1 for a maximally subsystemic model. And we've already heard that this overlap ratio goes to 0 with the dimension of the system, and also for fixed dimension with the number of states that we use in the experiment. And that's the path that we choose, because scaling the dimension is a bit harder. So we choose to scale the number of states. Now, a little problem here is as we increase the number of states, the number of measurements increases quadratically, because we have to pick those triplets, and that just increases quadratically. But nevertheless, as Matt pointed out, that's basically the easiest experiment you can do. Now, it turns out in practice, that's not quite the case. So we need a quantum system that is larger than a qubit, and our error bounds are very tight. So we have 0.3% error per measurement in order to still see something. Now, the way we do this is we use single photons from spontaneous parametric down conversion, and we dual encode them in polarization and path. So a photon comes in here, is polarized, then we set our path state, and on each path we encode polarization again, which gives us a Q quad. And then we reverse the setup to project on arbitrary Q quad states. So along the way, we produced some of the highest quality Q quad states in any architecture, actually, to reach this precision that we need for this experiment. And that's a typical results plot that you would find in our paper. So you have this S parameter, which is the upper bound and overlap ratio, our figure of merit, versus the number of states. And you have here the gray shaded area up there is where S is larger than 1. So that's where the maximally subsystemic models live. And the red bars are the theory predictions for perfect measurements. Now, we don't have perfect measurements, so if you put in some parameters of our experiment, that's more like what we expect. And the data agrees with that fairly well. And then we find we have 250 sigma violation of this bound of 1 here, which means we can conclusively rule out these maximally subsystemic models. And we also bound all the non-maximal models to below this value. To talk a bit about the scaling of dimension that I mentioned, our experiment naturally can produce Q trits and Q quads. So we compared that, and you see already for 5 states here, there's a big difference between the Q trit and the Q quad. So that's why we continued on with the Q quad then. Matt mentioned that this figure of merit that we're using might not be the best. So this is how it looks like if we use the overlap deficit that he introduced. Now you see there's a bit of a weird behavior, because the reason is our states are just not optimized for this measure. Our states are optimized for the other measure. We could get something like that, but as Matt pointed out, the set of states that we're using is just not optimal for this measure. So we're looking into finding different states that optimize the overlap deficit, so we can make a statement about this as well. And the other thing that we heard before is, if this is the average overlap of the states that we use, and it just goes down as we scale up. All right, but coming back to this, our results nevertheless suggest that this is maybe not the optimal place to be. And we might have to consider Copenhagen type interpretations or psiontic, or go to something more exotic. Now, our bound is just 70% at the moment, so we're working on improving this. And the major problems with the experiment is, on the one hand here, the wave plates, which are important for the accuracy of the experiment. And here where the big fat circle is, that's our polarization interferometer. So the stability of this is crucial. And we've done a couple of things. So actually most of on this list is already done. So we just improve the stability of this interferometer, more precise phase control, to push this bound down and push our error per measurement down, so that we can also go to larger number of states. And most importantly, I wrote here to explore the full state space. So what I mean by this is in the published results, we only used real valued states, which is enough to get this violation, but it doesn't give you the optimal values, even for our figure of merit. So by going to complex valued states, we can gain there. So I'll just summarize this part of my talk. So we've ruled out these maximally subsystemic models, and we also constrained non-maximal models to below this value of about 70%, which means that realist subsystemic models just cannot fully explain quantum indistinguishability in terms of these overlapping probability distributions. And yeah, Matt already mentioned that we can now either go to an ontic wave function if we want to maintain realism, or go to some more exotic ontologies. And these more exotic ontologies are actually part of what I want to talk about next. So that's some of our most recent results on local hidden variable models. So if we go a step back and look at what Bell had in mind, so we have this basic situation where we've got a source, we call this source lambda, and then we have two parties, Alice and Bob, who can perform measurements. So each of them gets a particle from the source and they can perform some measurements. And so they have measurement choices, typically 2, and then measurement outcomes, also typically 1 of 2. And then they observe correlations which violate the Bell inequality, and we're supposed to conclude something about non-locality. Now, what we can actually only conclude is that some of the assumptions going into these Bell inequalities must be given up, right? And there are quite a few of them. So obviously, we've got a direction of time. We assume space-like separation of these parties. We assume free choice of the measurement settings. There's a whole lot more, but Eric will talk about that next, so I'm not going to give that away. But what I want to do is just strip this to the bare minimum, which is these 5 variables. Right? And now we put them in a causal graph. So we have this directed acyclic graph where the nodes are random variables, and the directed edges represent causal dependencies. And then we've got causal statistical parameters, which specify how our variables depend on their graph theoretic parents. So the graph theoretic parents are quite intuitive. If you look at the variable A, the parents are x and lambda. So all the errors that come in. And now such a graph structure implies some conditional independence relations. So in this case, for example, we have that A is conditionally dependent on y given x and lambda. What this means is if I already know x and lambda, then learning y doesn't tell me anything new about A. Or in other words, Alice's outcome is independent of Bob's measurement setting, which we call parameter independence. And then also we have outcome independence, that Alice's outcome is independent of Bob's outcome, and free choice, that x and y are uncorrelated with anything in their past. And then we look at what the probability distributions are that are supported by this causal model, and we get Bell's local hidden variable model. And then people go to great efforts of testing this, and just yesterday we had this first looper-free experiment published. And what this tells us is that one of these assumptions going in there must be given up. And there has been quite some research into what can be given up, to what degree it has to be given up. I wanted to talk about a few of those. So one thing is the causal error. That's the basic assumption in these causal models, that a cause is in the past of its effect. Now, if you don't assume that, you can have, for example, the setting choice influencing the hidden variable. Now, I didn't say that before. These graphs are supposed to have a time error going from top to bottom. Now, one thing that we cannot describe in this framework is causal loops, because that's just not in that framework. Another thing is free choice. So we can consider superdeterministic interpretations where the hidden variable also influences our measurement choice. Or we can consider relaxing local causality, so we either relax parameter independence or we relax outcome independence, or both of them. And we want to look at this scenario where we relax outcome independence, meaning that Alice's outcome can have a direct causal influence on Bob's outcome. Now, looking at this model, we now have this error from A to B, but we have to quantify it somehow. And what we want to use for this is one of the basic concepts in this causal modeling program, which is an intervention. So if you think of the kind of the most primitive notion of causality, it's like I change something here and something happens over there, so I conclude there must be a causal influence. And that's what an intervention really is. So we want something that forces the variable A to take a certain value, and at the same time, it should break all the incoming errors. So we want to set a value for A, but it should be uncorrelated with everything else. So it should only depend on what we want to do. And then we can define this quantity, the average causal effect, which is basically the maximal shift of the probability distribution of B due to the intervention. And this average causal effect then quantifies the strength of this link, because it quantifies how much does B change when I do the intervention. And it gets rid of all of these influences. An interesting thing about it is it's defined in terms of observable quantities only. So that should be experimentally accessible. And the way we want to do this is we first need a source. So we take a Sagnac source of polarization entangled photons, which gives us a variable degree of entanglement. Then we distribute those two particles to our parties Alice and Bob, who perform the measurement settings, which are just wave plates in our case. And finally, they perform measurements and get measurement outcomes, which are defined by this polarizing beam splitter. And somewhere in between here, between the setting and the outcome, we want to place our intervention. So we can set this value of A, but break all the links coming in. So one way to do this in experiment, so you have to keep in mind that if you want to do an intervention, that's inherently device dependent. You have to know how your measurement device operates in order to set its value. So one way to do it, since our polarizing beam splitter acts in the Z basis, is we can just project onto Z eigenstates just before the beam splitter. Now this definitely forces A to take a certain value, but it doesn't quite break all the incoming errors. And the reason for this is that our Bell inequality, our measurements are in this XZ plane. But since they're all in a plane, what we can do instead is we can project on the orthogonal direction, which then breaks the error. So we project onto Y and then reprepare in Z, which breaks all the errors, but still allows us to deterministically set the value for A. And then if we come back to our quantity average causal effect, what we see is it has a direct relation to the CHSH violation. So that's the strength of causal link from A to B we need to explain the observed CHSH violation. It's just a linear relationship. Now we did the experiment, and what we find is something like that, which tells us that even if there is a little causal link, it's definitely not strong enough to explain these Bell correlations. Now that's using interventional data. But what we can also do is we can just take this model directly, write down the supported probability distributions, and then we consider a measurement scheme which has 3 inputs and 2 outputs, and compute the polytope for this, the probability polytope. And one of the facets of this polytope looks like that. So it's an inequality with a bound of 4, and it turns out that this inequality is violated by any pure entangled quantum state. So it means if we violate this in the lab, that rules out local hidden variable models without outcome independence. So these kind of models. And as an added bonus, it's actually symmetric in A and B, so we don't have to commit to a time order of these two. And that's what we find in an experiment. So this is when you take a fixed set of measurements. If you instead optimize the measurements for each state, then you can get this violation for every state that I mentioned before. And that's plotted versus a state parameter that goes from separable to maximally entangled back to separable. And yeah, that brings me to the conclusion, actually. So we showed that no cybersystemic model can fully explain quantum indistinguishability, and that relaxing outcome independence is not enough to rescue a causal explanation for Bell correlations. So let me just put up Andrew's advertisement slide, and thank you for your attention.